Hello and welcome to the 8.2 notes, and this is my favorite section that I teach, and this is dealing with the Pythagorean theorem, and the Pythagorean theorem is a relationship between the sides of a right triangle. So I'm going to zoom in here real quick, and I'm going to draw in a right triangle, like so. And a right triangle has one right angle, so I'm going to label that as a right angle. I'm going to call this distance right here, this length of the triangle that forms the right angle, one of the lengths. I'm going to call that the leg of the right triangle, okay? And then the other side that creates my right angle here, I'm going to call this a leg of the right triangle. And then what I do is I want to talk about this side here. And this side is the longest side of a right triangle, and that is always across from my right angle, and I'm going to call this the hypotenuse. Okay, hypotenuse. All right, so in a right triangle, my friend Pythagoras, which is what this theorem is named after, figured out that if you take the sides of a right triangle, okay, and I'm going to draw another one here. If you take the two legs squared and add them together, it will equal the hypotenuse squared if you have a right triangle. So I'm going to call this length A, I'm going to call this length B, and then I'm going to call this length C. And from the Pythagorean theorem, what we know is that if we take A squared, if we take that length A squared and we add that length B squared, then that's going to equal the length C squared, okay? And we've really been doing this all year long. We've been using the Pythagorean theorem to solve or to find the distance between 2 points. But what we can use is the Pythagorean theorem to find any missing side of a triangle. Okay, so typically what you'll be given is two of the sides, and we solve for the third. So sometimes you're given both lengths, and you're being asked to solve for the hypotenuse. That's what we've been doing for a while with coordinate geometry. But sometimes you're given the leg, one leg, and the hypotenuse, and you have to find the other leg. Okay, so what I want to do is talk about some special right triangles, okay? And we're going to call these Pythagorean triples. Okay, so Pythagorean triples. Okay. One of the most famous ones, one of Pythagoras' favorite triangles, and coincidentally, one of my favorite triangles, happens to be the triangle that has lengths 3, 4, and 5. Okay? And what we can tell, we can verify this, real quick. We can say that 3 squared plus 4 squared is equal to 5 squared. And so if I take 9 plus 16, we want to know, is that equal to 25? And 9 plus 16 is 25, so that equals that. And so, this is probably the most basic, simplest right triangle that we have that we consider a Pythagorean triple. And a Pythagorean triple, just to make sure we know what that is when the sides are whole numbers. When the sides are whole numbers. Okay, and by whole numbers, I mean that they're not decimals. Okay, so some of the Pythagorean triples that we have that we that we want to talk about. So let me write the examples of some. Is a 3, 4, and 5 Pythagorean triple. Another one would be a, let me do this, a 5, 12, 13 Pythagorean triple. Okay, another one would be 8, 15, 17. Let me choose a different color. 8, 15, and 17. And then another one, the last one is 7, 24, 25. So I'm going to do 7, and then 24 and 25. Now, these will all work, okay? These are all examples of Pythagorean triples, and this is the most basic, these are the most basic ones, okay? Now, what you can do is you can actually, enlarge these by a scale factor. You can dilate these triangles and make them bigger or smaller by, multiplying them by a factor. And so, if I were to multiply each of these lengths by, say, 2, then I would get a different Pythagorean triple, and I would get a 6, 8, and 10, okay? If I multiplied them by 3, then I would get a 9, 12, 15, okay? And so you get this ratio of sides that is basically just a 3, 4, 5, okay? The next one with a 5, 12, 13, if you multiplied that by 2, you would get a 10, 24, 26. Okay, if you multiplied it by 3, you'd get a 15, 36, 39, okay? If you took an 8, 15, 17, if you doubled that, then you would get 16, 30, 34. If you multiplied that by a factor of 3, you'd get a 24, 45, 51, okay? And so, and then the last one you would get would be like 14, 28, or no, I'm sorry, not 28, 48, and 50. Okay, if you multiplied these by a factor of 3, you'd get a 21, 72, 75. Now, the thing about the Pythagorean triples, guys, is that these, will pop up in future math classes. We see them in calculus. You'll see that, obviously, you'll see them in, trig and advanced algebra 2 trig. But if you recognize these relationships and know these different Pythagorean triples, at least these ones, then you don't really have to use the Pythagorean theorem if you remember these, if you know these and know how they work. And so we'll take a look at a bunch of examples, but this is kind of important just to recognize. You can always use Pythagorean theorem, but if you don't have to always use it, then it's kind of nice not to have to. So now let's talk about the types of triangles that you can get using some inequalities. Okay, so the other thing we need to talk about is the Pythagorean inequalities. Okay. And so in a triangle, okay, just in any sort of triangle, okay, lengths A, B, and C, okay, we know that if we have an acute triangle using some Pythagorean inequalities, if I take A squared plus B squared, then I know that this is going to be greater than C squared. Okay, then I know that I have an acute triangle if I have that relationship here. Okay, I know I have an obtuse triangle if it's the opposite. If it's A squared plus B squared is less than C squared. Okay, and of course you would have a right angle or a right triangle if you had A squared plus B squared is equal to the third side C squared. Okay, so and we'll kind of explore that, but these are the different types of things involved with the Pythagorean theorem. So it's really exciting. It's really good stuff. And let's go ahead and let's take a look at number 1 as a practice problem. And so whenever I do these types of problems, I always label my sides, and I always, we'll just call this A, B, and C. And then I always write out the Pythagorean theorem, and I say, okay, I know A squared plus B squared is equal to C squared. And so I want to plug in my numbers, okay? So A is 13, so I'm going to say 13 squared plus 23 squared is equal to C squared, okay? And now, so the whole thing I want to do is solve for this third side. And actually, let's not call it C. Let's call it X. So I'm going to call this X squared, okay, because that's what our value is. All right, so we want to solve for x. I mean, you can call it c if you want. So I need to go ahead and go through this math. And so let's go ahead and do that real quick. If I were to take 13 squared, that's going to give me 169. Okay, plus 23 squared is going to give me 529 is equal to x squared, okay? And then what I'm going to do is combine my like terms here. So 169 plus 529, that gives me 698 is equal to x squared. Now, if I want to solve for x, I want to take the square root of both sides, okay? And so you end up getting this. You get that x is equal to the square root of 698. Now you can try and simplify this. I can't really find anything to try and simplify this radical, so I'm just going to take the square root of 698, and that's going to give me an approximate value for x, okay, of 26.42. Go ahead and round to 2 decimal places. Okay, and this is my exact answer right here, and this is my approximate answer. And so either one's fine. I typically want the exact answer, but it's okay to have an approximate. Okay, let's go ahead and take a look at the second one. And this one is a little bit different. Okay, this one, I'm going to call this A, I'm going to call this B, and I'm going to call this C. Okay, and so in example 1, we were solving for the hypotenuse. In example 2, we were solving for one of the lengths. Okay, and so let's go ahead and write it out as a squared plus b squared is equal to c squared. And I'm going to go ahead and sub in my values. So a was x, so this is x squared, plus 21 squared is equal to 34 squared. Okay, and our objective here is to solve for x. So I get that x squared plus 21 squared is 441. And that's equal to 34 squared, which is 1,156. Okay, now to solve for x squared here, all right, this is a little tricky, but I need to get x by itself. So I'm going to move this number 441 to the other side. So I'm going to subtract both sides by 441 on both sides. And we get that x squared is equal to 715, okay? And so what I want to do is solve for x. I'm going to take the square root of both sides. And so we end up getting that x is equal to the square root of 715. Okay, and let me see if we can simplify that. And this one I can't seem to simplify at all, but let's just go ahead and take the square root of 715. And we end up getting an approximate value for x, that x is approximately 26.74, okay? So these are your answers, okay? This is exact, okay? This is an exact value, and this is an approximate value, okay? So let's go ahead and take a look at number 3. Now, number 3 is a little bit different, okay? Number 3, you know, they don't give us a right triangle. They give us an isosceles triangle. But what we've done is we've shown that we have a right triangle within that isosceles triangle, okay? Now, since this is a perpendicular bisector here, that's one of the properties of an isosceles triangle, that if you take the distance from the height down to the base as a right angle, it'll divide these two parts in half. So what we need to do is we need to realize that since this is cut in half, I know that these two segments are congruent. Okay, and if I divide 18 by 2, that's going to go ahead and give me 9, all right? So I'm going to go ahead and call this lengths A, B, and C, set up my Pythagorean theorem, and say that a squared plus b squared is equal to c squared, all right? But we just want to make sure that we're dealing with this triangle here, that we see a right triangle within our big triangle. So segment length A was 9, so I'm going to take 9 squared, okay, plus b squared. Now, b has the value of x, okay? That's what we're trying to find. So I'm going to call that x squared, and this is equal to 26 squared, okay? And so let's go ahead and solve this. And so we get 81 plus x squared is equal to 26 squared is 676. Okay, I'm going to subtract 81 from both sides. And I get a value of x squared is equal to, all right, 676 minus 81 gives me 595. Okay, and I don't know if we can simplify this. Let me go ahead and just take the square root of both sides. Okay, so first of all, we get that x is equal to the square root of 595. Okay, and I don't know, let me see if we can simplify this. And I really don't think that we can, so I'm just going to go ahead and take the square root of 595, and that's going to give me approximately 24.39. So 24.39. Okay, remember this is exact, this is our approximate. Okay. All right, so you'll see, various examples like this. I kind of wanted to show you a couple of them so you, wouldn't get terribly confused. But what I want to do is take a look at numbers 4 and 5, okay? And we are using Pythagorean triples to find x, and so you need to be thinking about these numbers here. Okay, and so we want to use these base numbers to try and recognize what we have to help solve for that third side. And so, what I want to think about here is I want to think about the numbers 24 and 36. Now, for some reason, this kind of looks like a 3-4-5 ratioed triangle. So if I take 27 and 36, both of those numbers are divisible by 9. So if I take 27 and divide that by 9, that's going to give me 3. Okay, if I take 36 and divide that by 9, that's going to give me 4. Okay, so this has the ratio of 3x and 4x. Okay, so both of those are being multiplied, the 3 and the 4 are being multiplied by a factor of 9. Okay, so then this would be a 5 times that number 9. And so x, okay, is equal to 5 times 9. So x, that missing side, is going to be 45. Okay, and so, the idea here is that, if I take 27 divided by 9, I'm going to get 3. If I take 36 and divide it by 9, I'm going to get 4. If I take 45 and divide that by 9, and I'm going to go ahead and do that, say 45 divided by 9, that's going to give me 5. So I have the ratio of a 3, 4, 5-sided triangle, okay? And that's how we kind of use these Pythagorean triples as opposed to using the Pythagorean theorem. That can kind of be lengthy, okay? So something to, ponder and think about. Let's take a look at number 5. Okay, on this one, we have a 42 and 150. This one looks kind of crazy, okay? Now, just from my personal experiences, I'm thinking it's either going to be, a 5, 12, 13 triangle or a 7, 24, 25 triangle. Now, here's why I'm going to think it's a 7, 24, 25 triangle. Because the hypotenuse here is 25. I can divide 150 by 25, okay? And I can get 25 out of that. If I look at my shortest side, which was a 7, 42 is divisible by 7, okay? So let's do something here. I'm going to take 42 and I'm going to divide that by 6. Okay, I'm going to take 42 and divide that by 6, and that's going to give me 7. I'm going to take 150. If I divide that by 6, let's see what that gives me. 150 over 6, just want to make sure that that gives me 25, and it does. Okay, so we want to find x. All right, now because I got 7 and 25 out of this, I know that this is a ratio of a 7, 24, 25 triangle. Now what I did was I took each of these numbers and divided them by 6 and 6, okay? So I would need to take this number here, okay, which the ratio of that would be a 24. So I would need to find out the side that I don't have, which is 24. Okay, I'm going to multiply that by 6, and that's what's going to be equal to x. So if I take 24 and multiply that by 6, then x is going to equal 144, okay? And that's all I'm doing, okay? So using Pythagorean triples to solve, you could always use the Pythagorean theorem, but it's a little bit easier if you don't have to, okay? I'm going to quickly do 6 and 7 real quick. We want to determine whether these sides of a triangle give me an acute, obtuse, or right triangle. So what I want to do is take the two smaller sides, take 10 squared plus 11 squared, and see what the relationship is between that sum and 20 squared. So if I take 10 squared, it's going to give me 100. If I take 11 squared, that's 121. And then 20 squared is actually 400. Okay, and if I take these two numbers and add them together, 20 squared, let me just verify that. Okay, that is 400. This gives me 221 and 400. Now what I know is that that the hypotenuse is much bigger. Okay, and so since the hypotenuse is much bigger, all right, I'm looking up over here and I know that this is an obtuse. So if the third side, the longest side, if they square it is bigger than the sum of these two sides, then we have an obtuse triangle. So this is obtuse. Okay, and the last one, on number 7, let's take a look at that. I'm going to take my two smaller sides, which is 5 times the square root of 2 squared plus 10 squared. What is the relationship between the sum of those two squares and my third side squared? So here's the thing I did want to go over with you. If I take 5 times the square root of 2 and square it, that means I'm taking 5 squared times the square root of 2 and square it, okay? Plus 10 squared, and we're trying to figure out what that is, and 11 squared. So 5 squared is 25. Square root of 2 squared is just going to give me 2, plus 100 squared, which is just 100. I'm sorry, 10 squared, which is 100. And what's the relationship between that and 121? Okay, and so what I get here is I get 25 times 2 is 50, plus 100. And what's the relationship between that and 121? And so you get 150. And the sum of these two sides here, or sum of those two squares, is greater than 121. So this is an acute triangle. So I hope you enjoyed this video. The Pythagorean theorem is truly my favorite theorem, and that's because Pythagoras is my friend. My dear friend that will never, ever, ever, ever let me down. So I hope you enjoyed this video as much as I enjoyed making it, and we'll see you soon. Thanks.